So the convention we've introduced at this point has sort of identified the change in energy from the perspective of either the system or surroundings. And so energy can be transferred between these two entities either as heat or as work. And in chemical systems, the way that work manifests is through this thing that we call PV work or P delta V work. And that's the sort of analogy to, say, what drives your vehicle. So when you combust fuel in oxygen in your engine, there's going to be some sort of piston inside of this engine. And if you combust this, you're going to get an expansion of gas in here, which is going to drive your piston upward. This piston can then do work on your machine, which in this case is a vehicle. And so we talk about work, which we won't talk about that much in this class, but just giving you a sense for how system and surroundings in a chemical system could transfer through work. This is how it would happen through pressure and then change in volume work, knowing that if you have gas in here, the expansion is going to increase the volume of the system. Okay, so when we're thinking about energy, we can think about energy as really the summation of heat and work, the change in energy, right? It's a contribution of both of those terms. Whether there's work or not, the energy has to be in one of these two forms. And if the work is really this P delta V term, we can substitute that directly in. We're going to substitute that as a negative term just to keep the directionality of positive and negatives the same. It's not that important that you know exactly why that is, but just know it comes from the positive negative convention that we've already introduced. So this becomes Q minus P delta V. We can rearrange this equation and solve for Q, and remember Q is heat in this case, and W is work. So the heat, Q, is then going to equal whatever the energy change in the system plus P delta V. So that's our heat. So this equation is true, and it's a ubiquitous, very influential equation. And there's sort of two real-world examples by which this thing can be operative. First is you could have this in a constant volume system. And by constant volume, I mean you are constraining your reaction to a vessel where the volume cannot change in any way, which is not like a piston. Right? This example, we're allowing the volume to change. Imagine that piston's fixed in space. That would be a constant volume system. In that case, we could rewrite this equation, and I'll put a sort of subscript here under the heat, Q, just to imply that this is under a constant volume condition. This is going to equal the change in energy of the system plus P delta V, but if the volume is unchanging, then the change in volume has to be 0, which means this term goes away, and the heat is the same as the energy. This can be done, but it's not really the case that we will start with in a general chemistry case. If you go on to take physical chemistry, you'll learn the constraints of the system and the value in doing an experiment this way. In our world, on our planet, all the chemical reactions that are occurring around us all the time are not occurring in a constant volume condition, right? If you are going to burn natural gas on your stove or burn sugar in your body or metabolize sugar in your body, those are all in systems that the volume can change. And so this is not necessarily an operative way to think about the energy change in a chemical system. Instead, what we most often have is a system that's constrained by pressure, or constant pressure system, right? The atmosphere around us that's pushing down on top of your body right now is fixed, typically based on sort of the weather and where you are in the world or your elevation. And so if you're at sea level, we say that you've got 1 atmosphere pressure pushing down on you. So if you go and try to boil some water for pasta on your stove, you're not constraining the volume, but the pressure is constant inside of your kitchen, and that's going to be imposed by whatever this external atmospheric pressure is. So in that case, we could rewrite this equation as Q sub P for a constant pressure system, that's equal to delta E plus P delta V, where this term is constant. And this is the type of expression that is most operative in the natural chemical systems that we'll be discussing and thinking about. And this is the one that we're going to think about in this class. So since most chemical reactions, at least in what we're going to deal with in this class, occur in open vessels and beakers and things that we're not constraining the volume, and the pressure is just whatever the atmospheric pressure is, we actually give this type of heat, which is the heat change over constant pressure. We call this delta H. And so really, and delta H is the change in enthalpy. Enthalpy here is just the specific flavor of heat. It's still Q. It's the same thing. So it's a specific flavor of heat that accounts for any change in PV work. So it's whatever the internal energy change is, including any PV work of this system. So it's just another sort of convention of nomenclature, but we use it most often because most of the systems we're dealing with are under constant pressure. So what we'll talk about going forward when we're thinking about the change in energy for a chemical system, say from high to low, this sort of picture, instead of writing it just simply energy, we'll write this often as enthalpy, because that energy change accounts for both the energy of the system and any PV work that might be done. You can imagine PV work can be inconsequential or even zero if you're thinking about reactions that are occurring in aqueous environments. So for example, like if you wanted to figure out what the energy change was for throwing sodium chloride into a beaker of water, there's no gas change, or there's no change in the volume, because we're going from NaCl solid to Na plus chloride, both of those aqueous. That's pretty inconsequential in terms of the volume change. But you could imagine that if you have a combustion reaction, that case you're taking gas and you're producing a different amount of gas, then that change in volume could be important. But you don't have to account for that, because that's going to be built in to this term that we call enthalpy. And so we'll just be accounting for energy change, but we'll be thinking about it from an enthalpy perspective because it builds that in, and then we don't have to think about it explicitly. So when we're thinking about the change in enthalpy, say on this picture over here, this delta H is going to be whatever the H, H final here minus the H initial. So we'll write this as H final minus H initial, which is the same as writing this as the enthalpy of the products where you finish minus what the enthalpy of the reactants were to start with. And since this is a state function, again, we don't care about the trajectory here. We just care about the beginning and the end and the overall change. And built into this change is going to account for the energy of the system and how those has changed in terms of the bonds, as well as the change in pressure volume work, if there is any. Okay, so let's bring these ideas together. How do we actually account for the energy change for a chemical reaction, the direction of energy, how it's flowing, where it's flowing, etc.? Well, we need that tool that we call the change in enthalpy, because that accounts for the actual energy change due to bond breaking and forming, but it also accounts for that PV work. So the place we start is to write out a thermochemical equation, which is exactly what you've done before. It's a balanced chemical equation, but it also has then attached to it what the overall enthalpy change for that system would be. So we'll start with this example of propane combustion to form CO2 and water. And the associated change in the enthalpy for this system is 204 kilojoules. And remember that this is not kilojoules per anything explicitly, but implicitly it means that this delta H pertains to the reaction as written. So we have this reaction, and we could think about it as 204 kilojoules of energy are released for every 1 mole of propane or 5 moles of O2 that are used in this combustion reaction. And so I like to think about this graphically always, so I'll just write H here instead of energy. We're starting here with propane, and we're going to end here with CO2 and water. We're going to traverse down here, and we're going to liberate 204 kilojoules of energy for every 1 mole of propane that's combusted. So this is really helpful to have the ability to tabulate and write out what this energy change is, but under what conditions is this energy change true, right? If you live in Colorado Springs and your house is at 6,000 feet, then this combustion reaction is occurring with an atmospheric pressure that's significantly less than 1 atmosphere, just due to elevation. But if you perform this same combustion reaction on your barbecue at sea level in the coastal California, then is this going to be the same for both? And the answer is no, it's not, because there's 2 different conditions there. So how do we actually compare the energy released across reactions? Well, we need to introduce this new sort of convention. So the way that we tabulate these values to be able to compare across systems independent of the actual conditions is to make sure that they're all tabulated using exactly the same conditions. It doesn't mean we can't compare across different conditions. We can and we will, but we need to start with a sort of common baseline. So we write a thermochemical equation. We write these in what's called the thermodynamic standard state, or sometimes people just call this, and I will too, standard state conditions. Those conditions imply that the reaction is conducted at 1 atmosphere of atmospheric pressure, so that's sea level, 25 C, so just a little bit warmer than room temperature, and any gases or concentrations of solutions are all going to be at 1 molar. So if we don't have a pure substance, we're going to assume that's 1 molar. And we're going to call this type of enthalpy under thermodynamic standard state. We'll say that the delta H here is going to be denoted by this degree symbol. That degree symbol indicates that the change in enthalpy is conducted or measured under the standard state. So for the reaction that I have written up here, this delta H is actually the standard temperature and pressure, the standard state for this reaction. And again, the 204 kilojoules refers to the reaction as written. So the question I would have for you is, what if I came in and I just doubled all of the reactants? And it's still a balanced chemical equation, but maybe not the simplest form of that. I'd say, well, there's actually 2 units of propane, 10 moles of oxygen, 6 of CO2, and 8 of H2O. So I just multiplied all the original coefficients by 2. Is this delta H at standard conditions, is this still true? Minus 204 kilojoules. Hopefully you said no, that's not true, because that 204 kilojoules was for the reaction as written. So what do we do with this energy change? Well, if the entire reaction quantity doubled, then the total amount of energy that gets liberated or used in the reaction will also get doubled. So we'll have to multiply this whole thing by 2, which would give us minus 408 kilojoules per 2 moles of C3H8, which would be the same as 204 kilojoules per 1 mole of C3H8 or propane. So it's really important. It's huge takeaway of this lesson is that the thermochemical equation will have some change in enthalpy or energy associated with it, but that is for the reaction as written. If you manipulate this reaction in any way by changing the coefficients for the stoichiometry, you then have to do the same sort of manipulation to whatever that energy change is or what. The same is true if you decide to think about, well, what is the energy change for this reaction if we run it in reverse? Down here I have the combustion reaction that we had originally, but I have that now running in reverse. So what that looks like is the opposite of what we had before, right? If what we had before was starting at an initial condition, which was propane plus oxygen, and ending up with CO2 and water, then the opposite of this reaction would be literally the opposite of the sort of state function going back uphill. And so we reverse the reaction. What happens to delta H? Remember, delta H in the forward direction as written was minus 408 kilojoules. So if we got 408 kilojoules when we went downhill, how much energy would we have to put in to run the reaction in the opposite direction? Hopefully you say the equal and opposite, which would mean that the delta H here would be positive 408 kilojoules. And that's going to be the case. If you manipulate a reaction, remember you have to manipulate its form. It's really important to think about the sign here as energy in or energy out. So positive sign means energy has to be put into the system. So we could write this like this: 6 CO2 plus 8 H2O plus 408 kilojoules. All of these are going to be required to get this reaction to run, whereas in the top reaction we would have yielding 6 CO2 and H2O plus 408 kilojoules we would get from the system that would then go to the surroundings. So let's use what we've learned so far to apply that to an example. So the question here is calculate the heat evolved from the following system, where you have 10 grams of H2 gas, hydrogen gas, burned in excess oxygen at STP. And STP is just shorthand that I use and most people use for standard temperature and pressure. All right, so that's telling us that we're going to be using the standard version of whatever the enthalpy change of the system is. So what's also given to us in the problem is the balanced thermochemical equation. So we have hydrogen plus oxygen burning to create water, and then associated with that we have our standard change in enthalpy, delta H naught, as minus 571.6 kilojoules. So what direction is the energy flowing just by looking at this value? Hopefully you can see that the energy is leaving the system, this being the system, the hydrogen plus the oxygen, and the surroundings being everything else that's surrounding the system. And so energy is going to be leaving the system, so you're going to get water plus 571.6 kilojoules of energy or heat. So we're being asked to calculate this heat for 10 grams of H2. What does this equation imply? Right, we've talked about this extensively so far. This energy change, this delta H naught, is referring to a start where we have H2 plus O2 and a final where we have just water, and we're traversing down here and we're getting minus 571.6 kilojoules for the reaction is written, right? That means for every 2 moles of H2, we get this amount of energy evolved. So do we have 2 moles? I don't know. We need to figure out how many moles 10 grams is. So how do we do that? Well, we need to do some dimensional analysis. So we can start with 10 grams of H2, and then we can say there are 1.008 grams of H2 for every mole of H2, right? Now we're in moles, so we're going to have quite a bit more than 2 moles in this case. Cancel our units, we're in moles of H2, and then we also have this relationship where we know that for every 2 moles of H2 that are combusted based on this balanced thermochemical equation, we yield this much energy. And so we can say 2 moles of H2, that produces minus 571.6 kilojoules of energy. I'm going to get rid of my moles here. Now we're in units of kilojoules. We can solve this. It's going to be 2.835 kilojoules of energy, of heat, which is what we're being asked to evaluate. Heat and enthalpy in this case are the same because there's no PV work, and that's going to be the case for all the examples we do. We're going to say that Q under constant pressure is the same as whatever the enthalpy change is here. So we just computed this enthalpy change. Let's check our number of sig figs here. Do we have the right number of sig figs? We had 3 here, so that's going to be our constraint, is 3. So this actually becomes 2.84 kilojoules of heat for the 10 grams that we started with.